Recently, our client Tommy met his banker to discuss continuing his father's restaurant legacy. In us, he found a partner that understood the importance of passing the torch. First Horizon Bank. Let's find a way. Go to firsthorizon.com/Tommy.
Attention car shoppers. Right now at South Carolina Federal Credit Union, you can get a new or used auto loan and pay nothing until 2024. And no payments for 90 days means nothing out of pocket going into the new year. Plus, we have flexible rates and terms, so you could make the best financial choice for you. Learn more at scfederal.org/auto loans. That's scfederal.org/auto loans. Certain restrictions apply. Existing South Carolina Federal credit loans are excluded.
Today's show is brought to you by ExpressVPN. Protect your online activity today and find out how you can get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Visit tryexpressvpn.com/space to learn more.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello again. Thank you for joining us on Space Nuts, the podcast about astronomy and all the strange and amazing things that are happening on Earth and in heaven. I'm Andrew Dunkley, your host, and joining me as always is Fred Watson from the Australian Astronomical Observatory. Hello, Fred.
Hello, Andrew. How are you going?
I'm quite well. You're looking dapper.
Oh, yes. Thank you very much. Yes. It's a shirt that I haven't worn for about 5 years, and I thought, I wonder why I never wear that.
Well, the thing they say about fashion is it always comes back. So, yeah. Actually, you're lucky it came back so fast.
Yeah, I'm still wearing things that came back in 1947.
Aren't we all?
Yeah.
Now, today, we're going to talk about an asteroid that passed by Earth very, very recently and what we may have learned from that. And an interesting concept in regard to time. We think about time in a certain way because of the rotation of our planet around its axis and around the sun and so on. But scientists look at time in a very different way, and they've been measuring mountains using atomic clocks. And a question from the audience about black holes and neutron stars. We'll get onto that very, very soon. Fred, we had an asteroid pass by. It didn't even wave. What's the story with this one?
Yeah, this is a slightly different one from the interstellar asteroid we were discussing recently. This is what's called a near-Earth object, a near-Earth lump of rock, round about 40 meters across. It passed by the Earth at a fairly safe but quite close distance on Friday the 9th of February. So it was one of these things that whizzed by, but unlike things that have been whizzing by the Earth for the last 4.6 billion years, we now notice them because we have, various
eyes in the sky. Yes.
Yeah, the eyes in the sky. That's right. So this particular one rejoiced in the name of Asteroid 2018 CB, Citizens Band, I suppose that stands for.
Could be.
We might talk about the nomenclature of asteroids some other time, but 2018 CB actually shot by around about a fifth of the distance between our planet and its moon, something like 65,000 kilometers.
That's pretty darn close, though, isn't it?
Yeah, it is. Yeah, it is. Oh, actually, I've lied to you. It was 69,700 kilometers.
Well, that makes a huge difference.
Yeah, nearly 70,000 kilometers. But as you say, that is close. It's about twice the distance to the belt of geostationary satellites that surrounds the Earth. At a height of 3,600 kilometers above the Earth's surface, we have this ring of asteroids.
Hello, Mandu. This is Kathmandu making his presence felt. We haven't heard from Mandu for a while, Fred.
No, he's been a bit vocal today. He's just complaining as he always does.
Fleas will do that.
he does know about geostationary satellites, and so he knows that 36,000 kilometers above the equator, in fact, there is this ring of satellites which are used to beam signals down to various parts of the Earth's surface. And the reason why they're at that distance is that that's the distance that a satellite takes exactly 1 day to go around the Earth. So it means that these spacecraft are always above the same point on the Earth's surface. So twice as far away as that, which is pretty close, really, is the distance that asteroid 2018 CB buzzed us a week or so ago. In fact, another one, actually a couple of days earlier, an even smaller one, which was probably only 15 or 20 meters across, called 2018 CC, that also made a close approach, but that was quite a lot further. That was 184,000 kilometers. What's amazing, really, Andrew, is that we can actually detect these things, because a rock that size, it's about the size of a small industrial building, sort of 20 or 30, 15 or 20 meters. It's really not very big at all. Perhaps a bit bigger than the average house, but still not much bigger than a house. And that's at getting on for 200,000 kilometers, something like, more or less half the distance to the moon. And it's still detectable by the telescopes that we have now. And that, of course, is a fairly recent phenomenon. It's only in the last 30 years that we recognise that the Earth's history has been modified by asteroid impact, and that it behoves us to actually keep an eye out on what's going past us. And the fact that we know about these things is really good news. Just to dot the I and cross the T, 2018 CB was discovered by the Catalina Sky Survey, which is
We've talked about that.
Yes, we have indeed. It's based in Tucson, Arizona. In fact, I visited there a couple of years ago. In fact, both these asteroids were discovered by the Catalina Sky Survey. It's funded by NASA. It's one of several fairly large facilities that are designed to keep an eye out for asteroids.
As a space nut, I have to ask you the obvious peanut gallery question, and that is, what if it did come close enough to break through the atmosphere? What would be the effect? 2018 CB, the 40-meter one, that's quite large. It would almost certainly have exploded in the upper atmosphere. It's something like twice as big as the one that exploded 5 years ago now over a place called Chelyabinsk in Russia. That was the one that, once it reached a height of 30 kilometers above the atmosphere, it just broke up, but with an extraordinary explosion, which meant it was 30 times brighter than the sun. And of course, that's what attracted everybody's attention on the ground and caused them to rush to the windows to have a look, whereupon the shockwave hit the ground a few minutes later and did a lot of damage and caused something like 1,000 injuries. Thankfully, nobody was killed, but
that's right.
This one's twice as big.
It is, and so it would have more than twice its destructive power, because these things scale with the volume rather than the diameter. So it would have been pretty dangerous, and it's not that much smaller than the one that we think entered the atmosphere in 1908 at Tunguska in Siberia, which devastated thousands of square kilometers of forest up there. I think it killed one person who was on the ground at the time nearby. But there's really, the only evidence for this thing was the demolished forest. It took a long time before people worked out what that was.
Yeah, and probably a saving grace that one came down over such a remote part of the planet.
That's right.
If this sort of thing came down over New York City or Los Angeles or Sydney or Moscow or Dubbo, there'd be something pretty catastrophic happening there.
Yeah, that's right. So the Tunguska event was 50 meters approximately, so rather bigger than this one, but still this one would have a pretty huge destructive power. I guess one of the interesting things about 2018 CB is that it was detected before it made its closest approach. So it was actually detected on its way in. Had there been any serious danger, that does give some time for civil defence measures, because at that stage you would know pretty well exactly where it was going to hit.
And our civil defence measures would be evacuation. We have no way of deflecting these things yet.
No,
so
not at the moment.
It would be a case of get out of Dodge and, find somewhere else to live.
Yes, that's right. Go to Dodge.
Yeah, come out here, check out the zoo, pat the tigers, walk away with one hand. It'd be awesome. All right, so it's good that we can see them, and good that it gives us time to react. And I guess the time will come where we may be able to deflect these things or even destroy them, but that time is not now. So better to know than to be able to leave than not know and go, what's that bright light in the...
Exactly. Quite so.
You're listening to Space Nuts. I'm Andrew Dunkley and he's Fred Watson. Now let's take a little break and find out more about our sponsor, ExpressVPN, rated #1 by Tech Radar. This is the one I use. I've been using it for a couple of years and I love it. When I joined ExpressVPN, they were brand new to the market, but I read a lot of reviews and did a lot of comparisons. And there was just something about their business model that I particularly liked. And a couple of years down the track, honestly, can't complain. Their interface is very easy to use. Their service is second to none. I've had to contact them a couple of times about certain things that I wanted to do, and they were brilliant. So you may be wondering why I do need a VPN at all. It's all about privacy. Do you really want big tech companies, governments and others knowing what's going on with your online activity? Even if you're having nothing to hide, it just feels downright creepy. I think you'll agree. And governments are getting more and more interested in what you're doing every day. And so, protecting your privacy is what VPN is all about. And how often do you run across websites that you want to get information from only to find that they're geo-blocked? This is becoming an increasing problem, but ExpressVPN solves that problem for you. Now, if you go to our special URL, you'll see quite a list of things this service can help you with, things you may never have thought of before. As I say, it's the one I use, secure, fast, and it just works. So protect yourself online today and find out more about how to get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Try expressvpn.com/space to learn more, and you'll find the link details in the show notes and on our website. Now, back to the show.
Roger, you're loud and clear here also.
Space Nuts.
Now, Fred, we're going to talk about time and atomic clocks and measurement. But people like me, the average person, think about time in terms of our day-to-day lives. We live our lives in seconds, minutes, hours, days, weeks, months, years. And that's our concept of time. But scientists see time in a very different way, and the universe has different elements of time. And we've got this really fascinating story about the use of atomic clocks to measure things. Now, atomic clocks you would normally associate with time. So what are they doing here?
You're right. You're quite right. To we humans, the passage of time is a fairly constant thing. But since the early part of the 20th century, when Einstein really revolutionized our thinking on time and space, we've known that time actually varies depending on what state you're in. And in particular, it depends on your state of motion, which is something that comes out of Einstein's special theory of relativity. Two people moving at different speeds will actually experience time in different ways. It really only becomes important when you're moving at nearly the speed of light, which you and I never do. No. So it's something that's fairly esoteric, but of course it comes very much into importance in things like the Large Hadron Collider, where you're whizzing particles around at almost the speed of light. But the other way in which time is affected, and this came from Einstein's general theory of relativity in 1915, That is what's called the gravitational time dilation. So it means if you put a clock, somebody watching it probably, in a gravitational field, for example, near the surface of the Earth, it will run slightly more slowly than if it is out in deep space. And it's not the fault of the clock. There's nothing wrong with the clock. It's simply that time itself slows down.
And you and I discussed this last week when we talked about the twin paradox. And
yeah, that's
you got
right.
two 4-year-old twins. You send one of them into space for 4 years at near the speed of light. He comes back 8 years old, and the other one's 104. That's the twin paradox, and
that is indeed.
It's quite extraordinary.
That comes about because of the special theory of relativity, the fact that things that are moving relative to one another have experienced time differently. But the gravitational one is really interesting, because what it means is that for us folk here on Earth, time is actually running slightly more slowly than if we were just in deep space and kind of hanging around. So is it possible to measure that? Because the difference is minuscule. It gets really significant when you're near something with huge gravitational potential like a black hole, but we aren't in a black hole. We're in a fairly normal-sized rocky planet with modest gravity. Is it possible to measure that gravitational time difference? And the answer is yes. We've had for some time, probably about the last 5 years or so, incredibly accurate atomic clocks. The current versions are called strontium lattice clocks, and they exist in some of the laboratories in the world. They're accurate to something like 1 second in 30 billion years. It is just extraordinary stuff.
That's amazing.
Which is kind of twice the age of the universe.
No excuses for being late for work.
No. Well, no, that's right. So what has happened is that physicists, actually based in Germany, I think principally, have built a portable version of this strontium lattice clock that can be moved around. And what they've done is they've taken it up a mountain and they've compared the time that it records with the time on a similar clock, which is actually in a lab in Torino in Italy. And what they're trying to do is show that because the Torino clock is about 1,000 meters below the level of the mountain clock, there should be a difference in time. And in fact, that difference, the expected difference, is such that if you had, let me find the figure here because it's quite staggering. If you have two clocks differing in height above sea level by 1,000 meters, you would expect one of them, the higher one, to run at a rate that, let me find the figure, it's in 10 years, the difference between them would be, I can't find it, but I'm pretty sure, yeah, here we are, 1,000 meters apart, you let them run for 10 years, one is different from the other by 31 millionths of a second. So 31 millionths of a second is what you're measuring over 10 years.
Yeah.
Over a year, it would be 3 millionths of a second.
But it proves that the gravitational effect on time is real.
That's right, if you can measure it. And I was going to say that such is the accuracy of these strontium lattice clocks that they have done. Yes, yeah. They've done it. They've measured that difference. They haven't got it quite as accurately as the 31 millionths of a second per decade would suggest, but they can detect the difference between them in the rate of ticking of the atomic clocks. It's spectacular stuff.
It is.
Really quite remarkable.
And this has been demonstrated in science fiction, and I'm going to refer to the movie Interstellar. That was a story about trying to find a way of getting humans to another planet because our planet was dying. And they were investigating one planet which was close to a black hole. And because of the gravitational effect of the black hole, this planet's time equated to every hour on the planet meant 7 years passed on Earth.
Yes.
Now, that's a pretty extreme example of it, but they were using gravitational effect of time to demonstrate the problem. And unfortunately, these people were stuck on the planet for 3 hours, 4 hours, and 28 years passed by on Earth. It's, that is a really interesting example of what we're talking about. I much prefer the 31 millionth of a second per decade issue. I can handle that.
yeah, we can handle that. That's right.
At least you're not going to get questions about where the hell have you been.
Yeah. But it is interesting stuff, though, in terms of demonstrating the validity of Einstein's general theory of relativity. Once again, it's fantastic proof that he was right on the money with his time dilation, gravitational time dilation.
Yeah, and I suppose it also draws attention to just how incredibly intelligent he was, because he didn't have the tools that we've got today. He would have had to do a lot of thinking, a lot of hard thinking, to come up with some of these concepts. So he was an extraordinary man.
Indeed he was.
All right, so we know about the effects of gravity on Earth and the effects of that on time, but you can't use it as an excuse for anything, particularly forgetting your anniversary. This is Space Nuts. Andrew Dunkley here with Fred Watson.
0G, and I feel fine.
Space Nuts.
Righto, Fred, we have a question from our studio audience, and this is from Greg in Sydney. And apologies for taking so long to get to this one, Greg, but we just didn't know. But he says, very entertaining as always, the latest reports of gravity waves are intensely interesting. We have now had several black hole mergers and one neutron star merger, which was fascinating for the follow-up observations in different spectral ranges: gamma, X-ray, UV, visible, infrared. When should we expect to see a black hole plus neutron star merger, and how might it be different? Wow, he's been putting a lot of thought into this, has Greg?
Absolutely, and it's a great question, Greg. You're right on the money that the first gravitational wave detections were indeed colliding black holes, merging black holes. But perhaps the more spectacular one was last year's collision of two neutron stars, which, as you say, all the electromagnetic observations tallied exactly with the gravitational wave observations, and it gave us a completely new insight into the mechanism of these collisions. Now, I don't believe there is any reason why there shouldn't be a collision between a black hole and a neutron star. The reason why I'm not certain about that, and it's partly because I'm not really a specialist in this field. But so what we've had so far has been collisions between similar objects, in fact, objects of a fairly similar mass. Mm-hmm. And that suggests that these objects were formed together, that they are what you might call a binary pair, and that binary pair has eventually lost its rotational energy, and so the two objects have collided, whether it's black holes or neutron stars. Whether there is a scenario where you have a neutron star in orbit around a black hole, I am not familiar enough with this, these kinds of studies to know if it's possible, but I believe it should be. So my guess is that eventually we will see a phenomenon which results in the collision of a black hole and a neutron star.
And Fred, a neutron star is quite small and very dense. It's quite different to what we know of as, if you're looking at our own sun, our own star, which we don't recommend you do without protection, by the way.
That's right. No, I should have. I'm sorry. I should have elaborated a little bit on that. So a neutron star is it's kind of the final stage before something gets to a black hole. If you've got a massive star that collapses at the end of its life, it can achieve a state where all the neutrons in it are packed densely together, and the mass of the star is not quite big enough for its gravitational collapsing force, if I can put it that way, to overcome the mutual repulsion of the neutrons one to another. So the neutrons hold the thing apart. They stop it from collapsing into a black hole. So neutron stars are a bit less massive than black holes, typically similar mass to the mass of the sun, but their diameter is of the order of 15 kilometers, 10, 15 kilometres, something like that, the size of a city. So the density is incredibly large. It's billions of tons per teaspoonful kind of thing.
That's amazing.
So that's the sort of secret here. If you had, say, a 30 solar mass black hole merging with a 1 solar mass neutron star, that would certainly produce gravitational waves. They might not be as spectacular as the 2 black holes merging or the 2 neutron stars, but what would tell you that was happening would be the exact shape of the gravitational wave signature, because it's the ripples through space themselves that tell you what you're dealing with. Their wavelength, their amplitude, how long they take to decay, how long they take to what we call chirp down at the end of that collision process. All of those things are now measurable with things like the LIGO gravitational wave detector, and with future gravitational wave detectors too. They're measurable, and so by studying those waveforms, you can actually deduce what it is that's collided. It's just thinking this through a little bit more. With a neutron star colliding with a black hole, really it's more a process of what we call accretion. The neutron star, I think, will be sucked into the event horizon of the black hole. That's the point of no return. Probably with very, very spectacular results. So you might also expect, as we did with the two neutron stars, to get a flash from this across X-rays and radio waves and visible light too, that can be detected. Once again, analysing that flash spectroscopically gives you much more information into what it is that's actually colliding. So I think Greg's question is a great one, and I think we can look forward to these things.
Oh, yeah, and there's every probability it's already happened. We just haven't detected it yet because the gravitational waves probably haven't reached us. So, and
that's
in
also
some
true.
Circumstances they may never reach us, but there's a distinct possibility that this has happened already, and we just got to wait for it to get here. And I suppose the answer to his question is, what would be different about it? A black hole neutron star merger? They'd be the same but different. That's the answer, essentially.
Quite so. Quite so. That's the short answer to the long one.
I always try to find the short answer. Always got in trouble for it at school. Andrew should elaborate more.
Yes is not a sufficiently detailed answer.
Well, they shouldn't ask closed questions. I'm a journalist now, and I understand these things. If they ask a closed question, you can give a yes/no answer, and you're not wrong.
Yes, that's right.
But that wasn't good enough. Anyway, that's the different story. Thank you, Greg, for your question. Hopefully we answered it to your satisfaction, and we would love to hear from more people about things that confuse them or they just want a bit more of a wholesome answer to in terms of what's happening in the world of astronomy. And Fred's the man to answer it for you. And if he can't answer it, he'll ask Mandu the cat, because Mandu is much more intelligent than the average human being.
He's fast asleep now, so that's how intelligent he is.
Well, I would suggest that taking a nap this time of the day is probably very intelligent.
Yeah.
Fred, as always, thank you so much. Great to chat.
Great pleasure, Andrew. Always good to talk, and we'll speak again soon.
We will indeed. That's Fred Watson from the Australian Astronomical Observatory. And thank you again for listening to our podcast, Space Nuts. Don't forget to tell your friends, follow us up on Facebook and Twitter, and share us. Please share us. We love being shared. And we will catch you again next time on the podcast known as Space Nuts.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Subscribe to the full podcast on iTunes, Audio Boom, and Stitcher, or your favourite podcast distributor. This has been another quality podcast production from Bytes.com.